In the previous video lesson where we covered gravitational potential energy, we studied an object that fell through a height of h in three different ways. Straight down, by sliding down a frictionless ramp that caused the object to displace at some angle, and by sliding down a curved track. Now in every case we found that the work done by gravity was positive. It came out to be equal to positive mgh to be exact. And therefore the change in gravitational potential energy was negative mgh. What we didn't investigate is what would be the work done by gravity or change in potential energy if the object were to rise. Well, if the object does rise, is lifted straight up, for example, then the force of gravity points down, but the displacement points up. So if we multiplied the magnitude of the force of gravity times the magnitude of the displacement, we'd also have to multiply it by the cosine of 180 degrees because the angle between these vectors is, of course, 180. They point in opposite directions. So we would find that the work done by gravity is equal to negative mgh. And therefore, the change in gravitational potential energy would be positive mgh. Whenever conservative forces are at play, we know the work done by that conservative force is always equal to the negative of the change in potential energy associated with that force. So the bottom line is, whenever an object falls, the change in gravitational potential energy is negative, and whenever an object rises, the change in gravitational potential energy is positive. Maybe we should replace the h with delta y just to make it easier, right? In other words, if an object's displacement is in the negative direction, then the change in gravitational potential energy will come out negative, right? So in that regard, we can just say that change in gravitational potential energy is just strictly equal to mg delta y, right? In this case, delta y being downward is a negative value, and in this case, delta y is a positive value. So regardless, this becomes a good definition for change in gravitational potential energy. It will come out negative when delta y is negative, and it'll come out positive if delta y is positive. Kinetic energy, as we know, is 1/2 mv squared. Now we have an equation, at least for change in gravitational potential energy. It's equal to mg delta y. Let me write that a little neater. So now we want to come up with an expression for elastic potential energy. So we'll take the example of somebody who pushes a platform at a constant speed across a smooth surface. So let's say that this is an ideal spring. Now what we mean by that is a graph of force versus displacement has a linear relationship, at least up to some point. Generally, any elastic material has this, what we call proportional limit, beyond which there's a nonlinear relationship between force and displacement. So as long as we don't stretch or compress objects beyond that proportional limit, then we say they're governed by Hooke's law, which suggests the force exerted by the spring is equal to negative the stiffness of the spring times the deformation of the spring. Now the negative sign is pretty intuitive, right? It's just saying that if we displace to the right, if delta x is a vector to the right, as the spring becomes more and more compressed, then the force is exerted by the spring, not the force exerted by the person, but the force exerted by the spring points to the left. Yeah, whenever delta x is positive, the force is going to be negative. So that's it. That's Hooke's law, and it governs ideal springs, and that's what we're going to assume in this case. So the work done by the spring is equal to the integral of f dot d, let's say dx, since we're pushing the object along an x-axis. That means it's the integral of negative kx dx. And so the work done by the spring is equal to negative 1/2 kx squared. Because it's an ideal spring, the force exerted, governed by Hooke's law, is another example of a conservative force, just like gravity. And so the change in elastic potential energy should be equal to the negative of the work done by the spring. So the change in gravitational potential energy is positive 1/2 kx squared. Now in this case, we've set a reference level where the initial position is the relaxed length of the spring. So it gets compressed to this value. And so x or delta x take on the same meaning. By the way, if the equation is elastic potential energy, energy stored in a spring, is 1/2 kx squared, then it doesn't matter whether the spring is stretched or compressed. If this person were to grab hold and pull the spring in this direction, so the coils become even longer, then the value of x or delta x would be negative, but that value gets squared. So whether the spring is compressed or it's stretched, the potential energy comes out to be a positive value. What if somebody were to push a block up an incline against a spring? Then you could have the case where, and pushed with constant velocity. Now we have a case where there's a change in two forms of energy, right? There's both the change in gravitational potential energy and a change in the elastic potential energy. So the change in gravitational potential energy, if the spring gets compressed to this position, we can just call that vertical displacement h, because the block is being lifted higher. The change in gravitational potential energy will be a positive mgh. If we see that the spring has been compressed this far, there's our value of delta x, or actually we can just say at this position x equals 0, and we don't actually have to call it delta x, we can just call it x. This would be positive 1/2 kx squared. Now the work done by gravity would then be negative mgh, and the work done by the spring would be negative 1/2 kx squared. So how much work is being done by the person, by their applied force? Well, if the block is pushed with constant velocity, then that means the change in kinetic energy is equal to 0, which by the work-kinetic energy theorem means the net amount of work has to equal 0. So the work done by the person plus the work done by gravity plus the work done by the spring all has to equal 0. So the work done by the person plus negative mgh plus negative 1/2 kx squared has to equal 0. So the work done by the person is equal to, well, if we add these values to both sides of the equation, then we find the work done by the person is equal to mgh plus 1/2 kx squared, which means the work done by the person is just equal to the change in gravitational potential energy plus the stored elastic potential energy. And so the work done by the person is entirely an effort to increase the potential energy of the system. Once the object is up at this higher position with the fully compressed spring, then the question is, how fast will the block be moving when it returns to its original position? Well, in that case, all we'd have to do is take the total amount of potential energy stored in the system at point A and set it equal to the amount of kinetic energy developed when it returns back to point B. But I'm getting ahead of myself a bit here. I'm referencing the law known as the law of conservation of energy. And we'll get to that in our next few lessons. Thanks for watching.